Lesson 1.8 focuses on conditional probability. We're going to begin by looking at independent events. In some of the previous lessons, we just looked at an experiment that involved one action. Now we're going to focus on experiments that involve two or more actions, or they're just two or more events that occur in a sequence. So an example, if we draw one card from a deck of cards and then draw another card, those are two separate actions. If we roll a die and then flip a coin, those are two separate actions. With these actions or these events, we've got to decide if they are independent or not. Two events are independent if the fact that event A occurs does not affect the probability of event B occurring. If your first event occurring does not affect or does not change the probability of this second event, then the events are independent. Two events A and B are dependent if the fact that A occurred does change or does affect the probability of B occurring. Sometimes we want to find the probability of an event occurring knowing that another event has already occurred. This is called conditional probability. Conditional probability is used when you wish to find the probability of a sequence of events. And you could have 2 events, 3 events, 4 events, any number of events. You're going to use the conditional probability. The formula for this is the probability of F and S equals the probability of F times the probability of S given F. In this formula, F is just going to represent the first event and S is going to represent the second event. If I read this formula with the meaning in it, I would say the probability of the first event occurring and then the probability of the second event occurring. That's the probability of F and S. That's equal to the probability of the first event occurring. That's the probability of F times the probability that the second event occurred given that or knowing that the first event has already occurred. That's that second part, the probability of S given F. That represents the conditional probability that S will occur given that F has already happened. So the probability of the second event happening knowing that the first event has already happened. And keep in mind that the probability of the first event, probability of F represents the probability of the first event. After this event occurs, we move on to the second event. These events do not happen at the same time. They happen one after another. So let's look at an example. A box contains 30 marbles, of which 16 are blue, 8 are red, and 6 are white. If we draw 2 marbles consecutively without replacement, find the following probabilities. So I want to know the probability of drawing 2 white marbles. So the probability of drawing 2 white is equal to the probability of drawing a white marble times the probability of the second marble being white given that the first marble was white. Well, let's look at the first probability. Of the 30 marbles, 6 are white. So when you reach in and draw the first marble, you have 6 chances of drawing a white one out of 30. So that probability is 6 over 30. Now you reach in and you draw a white marble and you keep it out. Since you're not replacing that marble, since you're keeping it out, that's going to change your probability for the second draw. First off, I only have 5 white marbles in the box now. So the chances of drawing a white marble is just 5 and not 6. And then also, instead of having 30 marbles in the box, I only have 29 because I took one out. So what I did in the first action changed the probability for the second action. Now if I multiply these, the probability of drawing 2 white marbles is 1 out of 29. Now let's look at the probability of drawing 2 red marbles. Well, that's the probability that the first one is red times the probability that the second one is red given that the first one was red. Well, in my box there are 8 red marbles. So for the first draw, for the first action, I have 8 chances of drawing a red marble out of 30 total. So the probability that the first marble is red is 8 out of 30. Now I reach in and I draw a red marble and I keep it out of the box. When I reach in for the second draw, my options have changed. Instead of having 8 red marbles, I only have 7. And instead of having 30 marbles total, I only have 29. So if I multiply these, the probability of drawing 2 red marbles is 28 out of 435. So now let's look, what is the probability of drawing a red marble followed by a blue marble? So that's the probability that the first marble is red times the probability that the second marble is blue given that the first one was red. Well, for my first action, for the probability of a red, I have 8 red out of 30 total. If I reach in and pull out a red marble, I still have 16 marbles that are blue. So for my second probability, the top number is a 16. But keep in mind, for the second draw, I don't have 30 marbles in the box, I only have 29. So the probability of drawing a blue for the second draw is 16 out of 29. If I multiply these, the probability of drawing a red and then a blue marble is 64 out of 435. Now for part D, the probability of drawing a blue marble followed by a white marble. So this is the probability that my first marble is blue times the probability that my second marble is white given that my first marble was blue. So with the first probability, there's 16 blue marbles out of 30 total. So the probability is 16 out of 30. For the second draw, since I pulled out a blue marble, I still have all 6 white marbles, but there's only 29 marbles in the box. So if I multiply these, the probability of drawing a blue marble and then a white marble is 16 out of 145. In the next example, you have a standard deck of cards. If you're dealt 2 cards consecutively without replacement, find the following probabilities. So I want to find the probability of being dealt 2 hearts. That's the probability that the first card is a heart times the probability that the second card is a heart given that the first card was a heart. Well, in a deck, I have 13 hearts out of 52 total cards. So for the first card to be a heart, the probability is 13 out of 52. Now for the second card, I have 1 less heart since the first card was a heart. So I only have 12 chances of being dealt a heart. And there's 1 less card in the deck, so I only have 51 total cards. If I multiply these, the probability of being dealt 2 hearts is 1 out of 17. In the next example, let's look at the probability of being dealt 2 jacks. Well, that's the probability that the first card is a jack times the probability that the second card is a jack given that the first card was a jack. Well, there are 4 jacks in a deck of cards. So the chances that first card is a jack is 4 out of 52. Now you assume that the first card was a jack. So for the second card, I only have 3 jacks left in the deck, and there's only 51 cards left in the deck. So if I multiply these, the probability of being dealt a pair of jacks or being dealt 2 jacks is 1 out of 221. Next, let's look at the probability of being dealt a heart followed by a diamond. Well, that's the probability that the first card is a heart times the probability that the second card is a diamond, given that the first card was a heart. Well, there's 13 hearts in a deck out of 52 total cards. So the probability of the first card is a heart is 13 out of 52. Knowing that that first card was a heart, that still leaves me with 13 diamonds for my second card, but I only have 51 total cards. So if I multiply these, the probability of being dealt a heart followed by a diamond is 13 out of 204. And in the last part, the probability of being dealt a diamond followed by a heart. Well, that's the probability that the first card is a diamond times the probability that the second card is a heart, given that the first card was a diamond. So for the first card, I have 13 diamonds out of 52 total cards. So the probability of being dealt a diamond is 13 out of 52. Then for my second card, I have all 13 hearts left in the deck, but I only have 51 total cards. So if I multiply this, I get the probability of being dealt a diamond followed by a heart is also 13 out of 204. Now consider the following problems. Suppose we draw one card from a standard deck, record the results, put the card back in the deck, draw another card, and record those results. That's just a long way of saying we're drawing 2 cards with replacement. So whatever card I draw first, I put it back in the deck for my second draw. So what's the probability that we drew a face card followed by a king? So that's the probability that the first card is a face card times the probability that the second card is a king, knowing that we just drew a face card. Well, there's 12 face cards in the deck. So the probability of drawing a face card is 12 out of 52. For the second one, the probability of drawing a king, knowing that the first card is a face card, since I put that first card back in the deck, it doesn't matter what it is. I basically am resetting the deck for the second card. So whether that first card was a king or not, for the second draw, I've got all 4 kings in the deck, and I have all 52 cards in the deck. So when you draw with replacement, the first action does not matter. It doesn't affect the second one. If I multiply these, the probability of being dealt a face card and a king would be 3 out of 169. Basically, if the 2 events are independent, the given part does not matter. If the 2 events are independent, you can use the following formula where the probability of the first and the second, it's just the probability of the first times the probability of the second. So let's look at another example. Let's go back to the box of 30 marbles. 16 are blue, 8 are red, 6 are white. This time I'm drawing 2 marbles with replacement. With replacement means that what I do on the first draw does not affect the second draw because I'm putting that marble back. I'm resetting the box of marbles for the second draw. So I want to find the probability of drawing 2 red marbles. That's just the probability that the first one is red times the probability that the second one is red. For each draw, I'm going to have all 8 red marbles out of the 30 possible marbles. So I have 8 over 30 times 8 over 30. So the probability of drawing 2 red is 16 out of 225. Now I want to find the probability of drawing a red marble followed by a blue marble. Since I'm drawing with replacement, that's just the probability that the first one is a red times the probability of drawing a blue. Well, there's 8 red out of 30 total, and there's 16 blue out of 30 total. So if I multiply these, the probability of drawing a red and a blue is 32 out of 225. Well, now let's look at 2 examples that are going to look similar, but there is a slight difference to them. A school survey found that 3 out of 5 students play sports. If 2 students are chosen at random, what is the probability that both students play sports? And the second one says, a survey finds that in a certain class, 15 students play sports and 9 students do not play sports. If 2 of the students from that class are chosen at random, what is the probability that both play sports? The first example gives us a general statistic that we can apply to each student. In this case, selecting 2 students are independent events. If the statistic is general that I apply to everyone, the events are independent. So the probability that both students play sports is equal to the probability that the first student plays sports times the probability that the second student plays sports. This is going back to an experimental probability where we're going to use the actual data. You know, all that I'm told is 3 out of the 5 students play sports, so I just assume that statistic will apply to everyone. So the probability that the first student plays sports is 3/5. The probability that the second student plays sports is also 3/5. So if I multiply this, the probability that they both play sports is 9 out of 25. In the next example, I'm given statistics that are specific to a class. A survey finds that in a certain class, 15 students play sports and 9 do not. If 2 students from that class are chosen at random, what is the probability that both students play sports? So this time, the 2 students are dependent events. The probability that both play sports is equal to the probability that the first plays times the probability that the second one plays given that the first one has already played. This would be similar to think of each student as being a marble in that box of marbles. You know, I select one student and I want to know if they played sports or not. Then I leave that student out and I reach in and I select another student and I want to know if that student plays sports or not. So this time removing the student from the class changes the probability, changes the probability that the second student actually played the sport. So the probability that the first student plays a sport, there's 15 students that play a sport out of a total of 24 students. And I get the 24 by adding the 15 and the 9. Now I choose one person that plays a sport and I pull them out. So the probability of selecting a second student that plays a sport, well, there's only 14 students left that play sports, and there were only 23 total students in the class. So the probability of the second student playing a sport, given that the first student played, is 14 out of 23. So in this example, the probability that both students play sports is 65 out of 184. For the next examples, you've got to decide if the events are independent or dependent, and then find the probability. If I'm given a general statistic that I apply to everyone, the events are independent. If I'm given a specific scenario for a certain class or a certain item, then those events are dependent. So a restaurant received a shipment of plates in which 4 out of the 100 plates were chipped or broken. If 2 plates are randomly selected, what is the probability that both plates are chipped or broken? This time I'm given a statistic for that specific shipment, and I'm asked for the probability for that specific shipment. So this is a specific example or a specific shipment, so the events are dependent. So the probability that both are broken is equal to the probability that the first one is broken times the probability that the second one is broken, given that the first one was broken. So what are the chances of reaching in and grabbing a plate that was broken? Well, there were 4 broken plates out of 100 total, so the probability that the first plate you select is broken is 4 out of 100. Now for the second event, you assume that you've pulled out a broken plate. What are the chances of reaching in and pulling out another broken plate? Well, since you've pulled out one of the 4 broken plates, you only have 3 broken plates left. And instead of 100 plates in a box, you've already pulled out one, so you only have 99 total plates. So the probability that they were both broken is 1 out of 825. In the next example, a restaurant knows that in any typical shipment of plates, 4 out of the 100 will be chipped or broken. If 2 plates are randomly selected from a shipment, what is the probability that both plates are chipped or broken? This time, the statistic that I'm given wasn't for the specific shipment that I'm asked the probability about. It's just a general or a typical statistic. So these are independent. That statistic is going to apply to each event. So since this is a general probability that applies to each plate, the events are independent. So the probability that both are broken is equal to the probability that the first one is broken times the probability that the second one is broken. So the probability that the first one is broken is 4 out of 100. Every plate has a 4 out of 100 chance of being a broken plate. So the probability that the second one is broken is also 4 out of 100. Remember, that statistic was not for that specific shipment. It was just a general statistic. So the probability that both are broken is 1 out of 625. In the next example, it's known that typically 16 out of 25 students will pass a certain test. If 2 students who took this test are randomly selected, find the probability that both students passed. Well, this is just a general statistic. So this is a general probability that applies to each student. So the events are independent. So the probability that both pass is the probability that the first one passes times the probability that the second one passes. Every student has a 16 out of 25 chance to pass. So both probabilities are 16 out of 25. So if I multiply these, the probability that both pass is 256 out of 625. The next example, on a recent test, 16 out of the 25 students passed. If two of these students are randomly selected, find the probability that both students passed. This time, the statistic that I'm given is specific. It's to that certain class, and I'm asked about the probability of that class. So these results are of a specific test, so the events are dependent. So the probability that both passes is equal to the probability that the first one passes times the probability that the second student passes, knowing that the first one passed. So I've got a class of 25 students and 16 passed the test. And I want to know, if I just randomly pick two of those students, what are the chances that both passed? So for the first student I select, I've got 16 that passed out of 25 total. So the probability of choosing a passing student is 16 out of 25. Now I take that student that passed and I've already selected them. So I pull them out of the class. And now of the ones left, what's the chances of selecting another student that passed? Well, this time there's only 15 students left that passed, and there's only 24 students total. So the probability that the second student passed was 15 out of 24. If I multiply these, the probability that both pass is 2/5. The next example, a survey of a high school math class found that 4 out of the 20 students had not taken the ACT. If you randomly select 2 students from that class, what is the probability that both students have not taken the ACT? These results are for a specific class, so the events are dependent. So the probability that both have not taken the ACT is the probability that the first student has not taken it times the probability that the second student has not taken it, knowing that the first student didn't take it. So in that class, 4 students have not taken the ACT. So my chances of selecting a student that didn't take the ACT is 4 out of 20. Now I've picked one student that hasn't taken the ACT. So that changes my chances of picking a second student that hasn't taken it, because I only have 3 students left that haven't taken it, and I only have 19 total students left. So if I multiply these, the probability that both students have not taken the ACT is 3 out of 95. Then for the last example, a statewide survey of high school students found that 4 out of every 20 students have not taken the ACT. If you randomly select 2 students from the state, what is the probability that both students have not taken the ACT? In this example, I'm given a general probability, a general statistic that applies to each student. It just said that in a survey of high school students, it didn't tell me which high school, how many high schools, how many students were surveyed. It just told me that 4 out of every 20 students have not taken the ACT. So these are independent. So the probability that both of the high school students have not taken the ACT is equal to the probability that the first one hasn't taken it times the probability that the second one hasn't taken it. I apply that general statistic to each student. So each student has a 4 out of 20 chance of not taking the ACT. So the probability that the first student hasn't taken the ACT is 4 out of 20, and the probability that the second student hasn't taken the ACT is 4 out of 20. So the probability that both students have not taken the ACT is 1 out of 25.